highlighting the use of neural ODEs to construct tractable generative models, using specifically continuous normalizing flows and a more constrained but highly scalable variant called residual flows. Right, so just so we're on the same page, I just wanted to give a very brief intro into how ODEs work, how they can be numerically computed in practice, and the motivation behind their use as a modeling tool. So it's easiest to compare to a simple integral, where we parameterize the derivative of some quantity h as a function f of an independent variable t. So the goal is to find the function, a unique function h of t, that has this derivative and also passes through some initial value h at time 0. Right, so the simplest method is to basically just approximate the solution with a series of Riemann sums. So on the grid of t values, we evaluate f basically all in parallel, and then multiply by the step size delta t, and then sum these quantities up. So while the true solution can only be written as an integral, in practice we would typically just have to approximate with a finite sum. Now, solving an ODE amounts to exactly the same problem, but now the derivative of h is expressed not just as a function of t, but also of h itself. This means we can't easily evaluate f because that would require having the solution to h already. So instead, as an analogy to the case of simple integration, we also start with an initial value for h at time 0, which lets us compute f at time 0. Right, so the idea is that we then need to sequentially build these Riemann sums. Right, we iteratively approximate h at the next time value, and then use this approximation to evaluate f, which lets us compute the next Riemann sum. So we can't do these Riemann sums in parallel anymore. Now the result is what is known as an Euler discretization. So in the limit as the step size goes to 0, this would recover the true function value. Now, this extra inconvenience of expressing the derivative as a function of the state h itself means that we can model a much more flexible family of amortized functions. Whereas with a simple integral, the initial value only affects the value of h as an additive constant. In an ODE, the state h depends non-linearly on the initial value. So this ODE parameterization is also often more natural. So in many domains, the change in the state of a system doesn't really depend on the time itself, but it depends more on the current state of the system. Right? So this type of parameterization is also more generalizable to unseen time values. So there's this often mentioned connection between residual networks and ODE solutions. There were early works by E and Haber and Ruthodel discussing the use of concepts from dynamical systems and applying them to improve residual networks. Now, the hidden units in the ResNet follow this formula, where each layer has a residual connection. So you apply f on the state itself, and then you just simply add it to the input. Now, this can be interpreted as a specific way of solving an ODE where f is a differential equation, specifically with a step size of 1 and the Euler discretization. Now, from this viewpoint, we can view a neural ODE as the infinitesimal limit of a ResNet, where the step size goes to 0. Okay, so next I'll talk about some subtle differences between solutions of ODEs and fixed step size discretizations, such as ResNets. And we'll find that neural ODEs are actually a more constrained class of models, but this leads to some very interesting applications. All right, so how expressive can a neural ODE be compared to just directly parameterizing the discretization scheme? And it turns out that ResNets are more expressive than ODEs, and this can be easily seen from an example. So suppose we want to fit the function, just a 1D function x squared, and we do this by taking x, specifically x as the initial value at some time h0, and then taking the state h at t for our prediction for y. So this is a trained neural ODE, and we can visualize the trajectories modeled by multiple inputs. So on this graph, t is the y-axis, and then h is the x-axis. So at the very bottom is what x is, and then at the very top is our prediction for y. So we see that while the neural ODE can transform positive values of x to x squared, it fails to transform any of the negative values. And this is due to a simple property of ODE solutions, that the trajectories conditioned on different initial values can't ever meet or cross each other. This is because the solution of an initial value problem is unique. And this uniqueness property is satisfied as long as f is Lipschitz continuous. But if we parameterize f as a neural network, as in the case of neural ODEs, it's basically always Lipschitz continuous, theoretically. Right? Because otherwise we wouldn't be able to apply gradient-based optimization to train neural nets. Okay, so this uniqueness property means that the mapping from H at any time to H at another time, this mapping is always a bijective mapping. So on the other hand, a residual network, or really any coarse discretization of an ODE, is a model that's not always constrained to always output bijective transformations. And as such, it can easily learn this x-squared function. In fact, it actually learns to merge both the positive and negative values in the first residual block. But we know that no ODE solution could ever model this, because this would imply that the solutions must cross at some point between the first and second residual blocks. This little experiment basically just shows that there exist functions that, while they look like discretizations of some underlying ODE, these functions don't actually correspond to the solution of any ODE. But because of this, the discretization, or the ResNets, is more expressive as a modeling tool. And ODEs model a more constrained set of functions. All right, so the implementation-wise, really the only difference is the use of an adaptive discretization scheme to ensure that the ODE is actually being solved correctly. Right? So we still parameterize F in both cases. During the course of training, the ODE, or rather this function F, becomes more and more complex. So if the ODE solver is not flexible enough, we won't be able to properly constrain our models. This is really only the case for fixed and coarse discretizations. But whether a discretization is coarse depends on how regularized F is. So if F changes significantly within a small interval, then the step size needs to be small enough to not miss that information. In this case, the solver we use acts as an adversary to the objective that we want to optimize. Its job is to ensure that the model remains within this constraint set, which often opposes the objective itself. So as a quick remedy to this, just to mention this briefly, the augmented neural ODEs paper by Dupont et al. Proposes basically just adding extra dimensions to the state. This still retains the continuous time properties, so your trajectories are still smooth, and the final state can still be used to recover the initial state. So that mapping is now, it's still injective, it's just not surjective. And furthermore, some recent works, particularly by this one by Zhang et al., have proven a sort of universal approximation theorem that states by adding just one extra dimension, your ODEs can represent any continuous function. All right, so to highlight a few applications before delving deeper into tractable general modeling, one motivation for ODEs was to be able to model irregularly sampled time series. So ODEs are a natural fit because we can compute the solution at any time value, and we don't have to adhere to a specific time discretization as would be in the case of like recurrent neural networks. So one of our follow-up works was to augment recurrent neural nets with the ability to interpolate its hidden state between observations. This was motivated by the presence of medical data, where observations of each patient came in the form of tests, which were done at very odd intervals. To efficiently handle this kind of data, we proposed modeling changes in the hidden state between your observation times. So some existing works used an exponential decay to create a sort of continuous time recurrent neural net. But this is really a special case of a very simple linear ODE. So we generalized this to using neural ODEs, and we note that this ODE transformation wouldn't lose any information about the previous hidden state because ODE solutions, again, are invertible. But they can still represent changes to the representation itself. So at observations, we can still use any RNN update formula to update the hidden state in a discontinuous fashion. Another benefit that some research groups have been pursuing is the modeling of dynamics with specific constraints. So here you would constrain the dynamics function itself. Specifically, the Hamiltonian and Lagrangian neural nets model physical environments that satisfy a conservation of energy. Finzi et al. Use transformations that are equivariant to Lie groups to design dynamics that conserve momentum. And then Resi et al. Have papers that construct physics-inspired architectures. This one in particular tries to mimic fluid, incompressible fluid simulations. There are some interesting applications when certain constraints are known regarding the target domain. And the neural ODE approach lets them train complex models within the confines of such constraints. And these constraints are typically easier to parameterize in the form of an ODE. And I think in the future, there will likely be more applications outside of physics. ODEs are quite prevalent in fields such as like economics, finance, epidemiology as well. Okay, so that was a brief general overview of some use cases for neural ODEs. So from now on, I'll start going into more depth on tractable generative modeling with applications to density estimation, training scalable generative models on, for example, images. Right. So one promising application of ODEs is to construct what is called a normalizing flow. This describes a family of tractable probabilistic models defined by a neural network generator. So central to normalizing flows is the use of an invertible function that acts as a mapping between some latent space Z and the data space X. Typically, the distribution in Z is chosen to be very simple. So you can efficiently sample from it, and you can efficiently compute its probability density. But with a very complex transformation, Z can still be transformed into any distribution with the same dimensionality. So due to the invertibility of this mapping, the probability density function can be exactly computed at X, unlike a generative adversarial network. So this tractability generally makes normalizing flows more applicable to a variety of scientific domains. And I'll be discussing a subclass of these models called continuous normalizing flows, or continuous time normalizing flows, which was first discussed in our original neural ODEs paper. So to describe this, I'll use a very simple 1D example. The problem setting is quite simple and it's quite general. So we just have a bunch of observations, and we want to fit a potentially very complex distribution. And we can parameterize this potentially very complex distribution by starting from a base distribution and then learning a transformation that's parameterized by a neural ODE. This distribution and the transformation are really the only two things that we explicitly parameterize. The idea is that the neural ODE redistributes and then transports mass from the base distribution at the bottom in order to define a distribution on X. And the relationship between the density in Z space and X space is given by this formula on the right that requires integrating over the divergence of F along the trajectory from Z to X. Normalizing flows basically have normalizing in their name because we always have access to automatically normalized density functions. All right, so what this equation lets us do is basically build powerful density models in high-dimensional continuous space. And it also provides us with a generative procedure for sampling from X. Right? So we can basically just sample from Z and then transport the sample into X space. So instead of a crude drawing, let's see if this works. Oh, there we go. Okay. Right. So instead of my crude drawing, this is a neat GIF that was created by Jesse, who co-authored the neural ODEs paper. So at the bottom is a simple Gaussian, so a standard Gaussian, and then at the top is that transformed density function. You can see from this visualization that the learned ODE is slowly transporting mass from a single mode into multiple modes. And in fact, each horizontal slice is a properly normalized density function. A continuous normalizing flow essentially defines an infinite set of distributions, one at each value of t. And without additional regularization, these intermediate distributions are really free to be whatever they want. But in fact, they can be regularized so that the intermediate distributions are more meaningful as some sort of interpolated distribution, which I will discuss in a bit. So first, I'll talk about this a bit. So in practice, the divergence of a neural network. So we're parameterizing F as a neural network, and the divergence isn't cheaply computable. The divergence is the trace of the Jacobian, trace being the sum of the diagonals, and the Jacobian is the matrix of first-order derivatives. So in the follow-up work by Graffel et al., we propose using the Hutchinson's trace estimator to stochastically estimate this integral over the divergence. The key insight here was that this trace estimator only requires vector Jacobian products, which are easily computable in automatic differentiation frameworks. It's typically implemented in most deep learning libraries. So this helped us scale continuous normalizing flows to actually high dimensions, as I mentioned it, to small images like MNIST and CFAR10. Okay, so going back to regularizing the trajectory. Some recent works have made a connection between continuous normalizing flows and solutions of optimal transport. Optimal transport essentially chooses the shortest and straightest path from Z to X. But this is typically done in a non-parametric fashion where you have some samples from Z and some samples from X. So Finlay et al. And Toyn et al. Proposed various regularization methods that, when applied, can steer the model towards learning optimal transport solutions. These regularizations essentially involve regularizing the Jacobian norm of F in some form. And also on the left is a diagram from Finlay et al. Where they show that the learned paths can be regularized to be straight, recovering a parametric solution to optimal transport. They also showed that this type of regularization can significantly reduce the required amount of compute for solving the neural ODE, implying that these solutions are less complex. And on the right is a figure from Toyn et al. With the same idea. So they showed that the base continuous normalizing flow learns curved trajectories, but with their regularization method, it approximates optimal solutions, optimal transport solutions. Right, so Toyn et al. Applied continuous normalizing flows in an interesting setting. So they used them to model cell dynamics of a developing human embryo system. So multiple observations were made, but only at very infrequent intervals of a few days. And so without explicit knowledge of which cells move to which location, this is essentially an unpaired problem where you have to figure out where, what the exact cell dynamics are. So the flow model learns how these cells transition across time. And since they observe multiple time values, the model can learn smoother and more generalizable transitions than optimal transport, which would actually only give you piecewise linear trajectories between the observed days. So once learned, the model can be used to perform interpolation to impute cell states at unobserved times. Another work by Young et al. Applied continuous normalizing flows to learn distributions over object shapes using a fully general point cloud representation. So for each class of objects, for instance here, a plane, a chair, or a car, they learn a latent variable that represents the shape. And then conditioned on this latent variable, a continuous normalizing flow then learns how to map samples from a Gaussian distribution into that desired shape. So this work just nicely shows the potential for using ODEs to learn complex distributions over point cloud representations. Okay, so next I'll talk about residual flows. So these are a much more scalable class of normalizing flow models that are sort of related to continuous normalizing flows. But they don't require solving a complex ODE. They don't require using a complex ODE solver. And they can simply use the Euler discretization. So they're kind of like a ResNet. So previously, we discussed that because the function f can become arbitrarily complex during training, it's necessary to make use of an adaptive ODE solver that can adapt to the changing complexity of f. In practice, this usually amounts to choosing smaller and smaller step sizes as training goes on. Now, it turns out that if we explicitly constrain the set of functions that f can learn, then we can actually get away with using large fixed step sizes. We can show that if the Euler discretization, if we use the Euler discretization, the step size and the Lipschitz constant of f need to be in an inverse relationship. So without loss of generality here, we're always going to choose a step size of 1. This means f simply needs to always be Lipschitz less than 1. So based on this, we constructed invertible residual networks that have the same functional form as a standard ResNet, but it's constrained to always be bijective. And this visualization on the right shows that the standard ResNets might end up learning reflections in the middle, while invertible ResNets are constrained to never cross paths. All right, so once invertibility is satisfied, we can again use the change of variables formula to create a normalizing flow to create a tractable general model, right, based on residual networks. By doing so, we actually obtain an infinite series, which is shown in red. This is the likelihood of your outputs. So written in this form, exact computation would be basically infeasible, as that would require infinite compute. Right? But this formulation of the log density opens up the possibility of using efficient estimation methods. So you might notice that there's a trace inside the infinite series. So we can use the trace estimator. But the main problem is this, how to compute this infinite sum. So the approach we take is quite general, and it's actually, it's appropriately named the Russian roulette estimator. So here we do require that the infinite sum converges absolutely. And what I'll describe is actually quite a general approach that can be applied to estimate solutions of implicit problems, solutions of any limiting quantity. So maybe this can be your takeaway from this talk, even if you don't particularly care about general modeling. Okay, so we'll estimate this infinite series, delta k, one term at a time. So suppose we always estimate the first term, and then we flip a coin with probability q, and if it's heads, interpret it as a success or the value 1, we'll stop evaluating any more terms. Otherwise, we just keep evaluating. But if we continue, then we need to upweight the remaining terms, infinite number of terms, by a factor of 1 over 1 minus q. This is essentially because when we take the expectation, this reweighting cancels out with the probability of the outcome. And the result is just a very simple unbiased estimator. But something very interesting has happened here. So in computing this estimator, there's now a probability of q that we only need a finite amount of compute. But this estimator still has a non-zero probability of requiring infinite compute. So to take this even further, we can apply this trick over and over again to the remaining terms, sampling a new coin toss for every outcome that we have to continue. So we can do this. So we can obtain an estimator that uses finite compute with probability 1. And we basically just need to apply this trick infinitely many times. So instead of doing that, we can actually sample the coin tosses, we can reparameterize this estimator to basically sample the first successful coin toss. And this will be a distribution over the natural numbers. Right. For every term that we compute in this sum, we only compute it because we failed k minus 1 coin tosses. So we need to weight these terms appropriately by that probability. And then the final unbiased estimator, when we apply it to residual invertible ResNets, so the final unbiased estimator for this log likelihood uses two sources of stochasticity. So one is from the trace estimator, shown in blue, and then the other one is from this Russian roulette estimator, which is the one in orange. So we call this a residual flow because now it's basically a ResNet, but it's also a normalizing flow model with one constraint, which is that the Lipschitz needs to be less than 1 for every residual block. So this unbiased estimator is also actually very efficient in practice. We specify P of n as a shifted geometric distribution that only has an expected compute of only 4 terms. And the geometric distribution has a very light tail. So we sample large values. So the chance of sampling a very large value of n is extremely small. All right, so actually another way, there's another way to approximate this log P of y is to simply always truncate at a fixed n. Right? But this is a biased estimator because it doesn't take into account any of the terms that are larger than n. So here's a comparison between training using that unbiased estimator with the Russian roulette and just training using a fixed truncation at some n equals to 10. So the biased estimator used here during training, it's the red dashed line at the very bottom. It converges to something that's less than 1 base pair dimension. So base pair dimension it is a unit of the negative log likelihood. This is something we want to minimize. But the actual log likelihood was actually something that's closer to 10. Closer to 4. This is something we used the unbiased estimator to compute. And this log likelihood doesn't actually converge at all. This is not an effect of overfitting to the training data sets or anything like that. It's an effect of overfitting to the bias in the estimator itself. So in contrast, by using our unbiased estimator, the training is quite stable. It's the blue lines. And we can reliably train the model without having to worry about any sort of bias. So one potential downside of this estimator, though, is the variable compute and the variable memory cost. Variable compute isn't really a big deal because the expected compute is still constant throughout training, and the variance in walk-log time per iteration is actually quite small. But the variable memory is difficult to deal with because the maximum amount of memory required during training isn't known. This is because there's always some probability of sampling a large enough n and then suddenly running out of memory unexpectedly during training. So to remedy this, we used a different but equivalent gradient formulation. So we can first rewrite our estimator to emphasize the gradient path. So the constants are all grayed out, and then we can just set them aside. If we estimate the log likelihood like this, and then backpropagate through the estimator, right, through the solver of the infinite series, we need to backpropagate through every single term in that series. This implies that we need to keep all the terms in memory. So the memory cost scales with n. Alternatively, we can actually analytically differentiate the original infinite series and then formulate the gradient as an alternative Newman series. We can then still apply the same unbiased estimator tricks to obtain an unbiased gradient estimator. This is a similar trick to the adjoint method for backpropagating through ODE solutions, or the implicit function theorem for backpropagating through fixed point solutions. Essentially, we manually derive the gradient as an alternative formulation instead of backpropagating through the solver itself. We can then apply the same tricks to estimate this infinite series that converges to the gradient. So the biggest advantage of this estimator is that now we don't need to backpropagate through the estimated series. So we only need to backpropagate through a single Jacobian term, which is weighted by this estimated series. Right. So do you understand the impact of this gradient estimator? This plot shows, I think I'm running out of time. Yeah, okay, so this plot shows the amount of memory that would have been required if we were to compute 10 terms of the infinite series. So the summary is basically, if we don't use the alternative gradient estimator, that would be the blue line, and then that would basically be intractable if we try to scale to larger models. So the combination of a few tricks, including the gradient estimation, basically allows us to train very large models with as small amount of memory cost as possible. The quick summary for Residual Flows is that this invertible ResNet architecture constrains the dynamics function, and then that lets us use a fixed discretization. This also translates to a fixed compute cost, whereas with an unconstrained F, we would have had to use adaptive solvers that typically increase in compute costs as F becomes more complex during training in the form of a neuro ODE. We also have memory efficient gradients for scalable training. I'll spare you the table numbers, but essentially we just scaled up to large images of 256 by 256. So this is all trained using the very simple maximum likelihood training objective. This was also trained using smaller models compared to previous normalizing flows because residual blocks are more expressive than with like a coupling block. Right, so the brief one-line summary, one-line takeaway is simply to don't be afraid to take limits. There are existing tools that can efficiently compute or efficiently estimate these limiting quantities. So using limits in your model or the objective is actually more tractable than you might think. So an ODE perspective also helps introduce new methods that are like simple or yet flexible with a wide variety of applications. And I think this ODE formulation can encourage the use of deep learning in other scientific fields in the future as well. That's all. Thank you for listening.